ish. So the next step, you want to do EDA, right? Your exploratory data analysis. So now we're at the stage whereby you need to explore data. The first thing that I do always, and most of the people, if you look at the tutorials online and some other people, they say DF. This is my data frame, so it's called data. Yeah. So you can call it DF as head. So head will give you, like you've learned, the first five top rows and columns in your data frame. And you will see that you've got different columns that have different numbers. At this stage, you don't know what they mean. And they've got medical terms, and the question that we asked ourselves was given this data, so if I got your data about, if I measured your pelvic incidence, your pelvic tilt numeric, if you dive deep, you'll see it's just some bones angles and stuff. I can then predict whether you've got you normal or abnormal without you going to. So the point is that the orthopedic surgeon in this case will then be able to predict whether you're normal or abnormal. And if we find that you are abnormal, then we have to find what abnormally you have. Maybe you've got, I don't know, right? Arthritis. So head will just show you the first five, and we've got these degree of this word. We've got both positive and negative numbers, and this is the radius. You can clearly see from your data set that you've got numerical and categorical data. The second thing that you want to know is to just get an information about your data, which you've learned about this as well. If you look at carefully, you'll see that everything is 310 except this, right? So there's some missing values there. We need to do something about that. Here's the explanation. You could also do something like, because we know that we've got categorical and non-categorical data, let's just see the split between this column called class, so it could be classification. So you can run this, you'll get this. Probably you guys don't have this in your notes. And the other thing that you'll want to see is called describe. This is before you do, before you do, crazy exploratory data analysis. You can clearly tell whether your data needs some polishing by just looking at these three things. And we've seen that there's some missing values. We've picked up on that. We've seen that we've got categorical and non-categorical. And this only takes in numeric except the categorical value, which is a describe. Of course, we cannot find we can find a count, but we cannot find a mean and standard deviation of categorical data, with reasons that we explained in the earlier workshops. And then you can see that if you want to see the distribution of your data according to each column, you can clearly tell that this ranges between, has a minimum of minus and a max of this. So we should, whenever we receive data from a patient or from somebody based on what we this, we know we're expecting a value within this range, so that when you measure yourself in the future, we know that there's a problem before we even do anything. So if I get a value like 1,000 here, I know that maybe it was an incorrect measurement or something. So by just looking at this, I have an idea. And another way of doing, trying to find the relationship within your features or your inputs, depending how you name it. So people name it different ways. So some people say feature, some people say input, and then your target variable will be your output, depending on how you name it. So yeah, it's just a terminology. Now, who knows what this means? Yeah, it looks like a confusion matrix.
What's going on?
You need headsets.
Yeah.
Okay, can we give that gentleman a headset? He's not interested. So what you can remember at this stage, you're not making any decisions, right? You're trying to see what the data is like, right? And doing a scatter matrix will show you a relationship between each input in your data frame, on your data, right? And we can see with respect to the class how each one behaves, and we can start comparing the results. And you can see if I compare the pelvic incident with the pelvic tilt numeric, I have somehow a linear relationship with the normal abnormal being red. So we can see the scatter of people who are abnormal based on their value, right? Why would you want to do this? Does anyone know? Why would you want to compare have a scatter between two values or a relationship between that? Why is this scatter matrix, important? Okay, besides that, okay, I was not planning to talk about this, but you can see if the distribution and what each value compared to another one, where it puts you, whether you normal or abnormal, right? And remember, at this stage, we have not done any feature selection, we have not done any prediction. We just say, based on the data that we have and how the doctor or the orthopedic surgeon classify the previous patients that were there, where do they lie according to each variable? Why will this be important? Let's say I didn't want to build a complex model. From this, I can quickly go build a linear model based on this and stop complicating things, right? Because I can see there's a linear relationship. Maybe there's somehow a relationship here. It's not linear, but it's you could say secular or something like that. So based on what feature I want to use, let's say I want to use two features, I can build a model quickly based on what features I wanna choose. So this one, it will be somehow, you can see the green people, green, they are normal. You can see here the normal people, they are around there. So we wouldn't fit a linear, we would fit something like a polynomial degree or something like that. That will fit this type of data. Okay, cool. Is there any problem with this? So here we just say, can you see the count plot or how many abnormal people I have versus normal? Right? This is quite very important because remember we said this is a medical data set, so you can introduce some biases into your algorithm, and you don't want to do that, right? You don't want to say somebody's normal where else is abnormal. And you don't want to say someone is abnormal where else they're normal. So I hope that makes sense. There's people who are normal and they are abnormal, you see, when we see them. So our classification algorithm in our brains, when you look at them, it's like, this guy is abnormal. So you don't want to do that, especially when you build this thing. Remember, we realized that there were missing values. I made this on purpose, just like Python stuff. The initial data set, everything was filled, of course. But for the purpose of learning, and you can go through the tutorial and the notebook on Kaggle and stuff, you will see that this is 0. So we want to check which features have missing values, right? How can we do that? You say data, and Python is null, and then you start counting in each column how many missing values you have, which makes sense because here we saw 310 minus 305. There's like 5 things, which makes sense, right? Where are we? Oh, here. Now, maybe I should ask you a question. How do we then fill in missing values here? Let's ask someone. How do we fill? It's a numerical value. How do we? A mean. Why? Huh? She's saying we should use a mean. I'd argue and say a median or something complex.
A mean because the mean is average, right? So we are assuming that maybe those missing values are in the same range as those values that were not missing, something like that.
Okay.
So, for example, in age 25, maybe someone is missing, and then we may take the average of the two. Maybe we can assume that that person belongs to the same range as those people.
Okay, so she's saying we can use a mean, use a median if you want to. How do you write a median? Use a median if you want to. Still saying. So she's saying we can use a mean because she made an example and she says if you've got 2 individuals that are within age group, you would assume that the missing values are within that average, right? Okay. So it's a similar strategy, but things do get complex, right? Whereby you cannot use a mean, whereby you cannot use a median, right? Because I know a person who's writing a paper on this, saying that how do you find an algorithm that predicts missing values, right? So this is complex because you have not built your model yet. So you need to find an algorithm that predicts the missing values, not just using a mean, because it can get more complex than this. You can get, more complex than this. But for the purpose of this tutorial, using a mean or median should be fine. So a mean will still keep our mean overall of that particular column the same. And in sklearn, there's something called, okay, question. Now, what if, yes, let's ask someone else. What if the missing values were categorical? So, let's ask you. So, let's ask guys from this side. What if the missing value was categorical? You looked at me. Answer. What if the missing values was categorical? No idea. Anyone else? Random selection. So are you saying that, let's say for example, if these were males and female, so you're gonna randomly select mixed males and female? Let's think about it. Guys, you did the workshops, right? So the answer is somewhere there. So that gets interesting if the missing value is categorical, because you cannot find the mean of male and female. So how do you solve that? Other. So I've got male. Nah, let's not put. Okay, there's other. Okay, in gender. So. Okay, so she has an answer. Yeah, perhaps you could do that. You could do some k-means, but you need to remember, things need to be justified, right? The purpose of this tutorial is not just to say we apply. Whatever we're going to do, we're going to justify why did we choose this value. So in the previous workshop, SVM worked. So now we need to justify why. So I agree with you. So you would have to justify why we chose a k-mean, right? Maybe you looked at the nearest neighbors and you're like, okay, so this missing values has a relationship like this. Probably it's a male or female, right? Which is a good example, yes.
But then when we also check how important the data is towards what you're working to, like your final output.
Yeah. So I wouldn't want to drop the classification. So there's different solutions, right?
Five values you can do.
Depending, like what he's saying. So other people, and this I don't like, because people just say, there's missing values, drop, right? Let's continue to work. It's good, but you need to justify why you're dropping all those columns, right? There are cases whereby you'll be like, let me just drop all these columns, because they might not be significant to what what you're trying to achieve. Or maybe, let's say 40% or 50% of those columns are missing. So even if you put a mean, they will still not change much, because you have like 50% of that column missing or 60%. So there are cases where we want to drop those columns or features. So yes, k-means, and the gentleman here, he also suggested a good answer. So the idea is that there's no one general rule. There's no golden rule, right? There's no rule that says, if you get this, drop the columns. Not like that. You need to justify why you're doing that. But I know, being on DSIDE, want things to work, I'm like, this thing is not working. I must do a k-means. Nah, I'm dropping this. Right? But it will be a good exercise if you try and justify why you want to do something. Okay, so, sorry guys, I can't see you from this side. You get an error. Really? Which one are you running?
Oh yeah.
There's a copy. I've got two. This one. Okay, I guess. Okay, I'm the one who manually went there and like remove, because the original data set was complete. But you get the idea. Okay. So maybe it's on mine. I'll send you the one that doesn't have. So here you put. This case was easy because we knew which column had missing values, right? It was this, and then we made it an NP array, and then there's something called an imputer function, which comes from sklearn preprocessing. So you import imputer, you put the missing values and say NaN, and what strategy you want to use, median or mean, and the X is going towards your column, and then I just created this column and fitted. So I'm fitting this into that, then reshape, make it a column back, and you will see that there's no missing values if you look at this array here. Everything is complete. But now that's an array, so we need to put it back to the data frame. Then you put it back to the data frame, and then when you run the same function, you don't have missing values. So at this stage, what you've learned is got a data which you knew nothing about and you did some research on the internet and stuff and things like that. But if you have guys who know what the data set means, so in their group you can ask them, so which is better? What does this mean? You understand? And things like that. And which is cool. So who's confused, who's not confused? Now, here's the interesting part, right? So, now this is where data scientists, they get happy because they're doing cool stuff. Then it was like, data. It can be stressful sometimes. Now, I know you guys did K and N. K, look at the closest labeled data points. And we know that is a classification method. I don't know what and X is our features, and Y is our target variable, which is our class. Right? So we try to use our inputs to predict whether you normal or abnormal, which is our target variable. And that was our question. That was our initial question. We'll answer the rest of the question. And the number of neighbors is K. The coolest thing about K and N is just that you can just chuck in your X and Y and start predicting. So what I did is that I said my X, so in Python, you guys did tutorial in Python, so my X is this part here, my Y is this part here. So what I'm saying is this: locate all the data columns except class, right? That's my input, right? So you cannot feed your answer to find the answer, so it doesn't make sense. So my X, that's my input, everything except the class. So you remember this method, right? Everything, all the columns except the class. Does this part make sense?
Yep.
And then my Y, the class only, which is the classification, whether you abnormal or not. So go to the data frame, everything, which is a class, and the KNN, which is this. And if you go to sklen, or what we're using, this is what Vaughan might have done. Choose 3, right? Not justified. No one asked me why I chose 3. Let's just put 3, right? And start predicting. And yay, I can tell who's normal and who's not abnormal. But there's something problematic with this. Right? Oh, okay. Who's abnormal and who's normal? Thanks. Thanks. But we haven't fitted our data. We haven't splitted it, right? So we need a measure to say how well is this thing performing, right? Because you see, I just did it in like 3 steps. I was be able to predict. But I know amongst us, there's people who are normal, or else they're abnormal. So we need a metric to measure, to say how well is this thing performing, right? And like I said, is accuracy the best metric to say whether an algorithm is performing best or not? That's the question. Hello. Hi. You okay? I asked a question. Is accuracy, we're going to take a 2 minutes break now. Maybe you guys need to discuss things. Yeah, so I'll ask anyone randomly, maybe you just, is accuracy the best metric to describe or measure our model performance? That's the question. Okay, just send me a message. Let's just take a 2 minutes break. I just need to reply. I'll ask anyone randomly, so it's a random selection. Right. You guys can decide that. You can go drink water or something.
Depending on what you're looking for, right? But accuracy is not there. You need to understand. You need to understand transition, sensitivity.
So it's not actually accuracy is not because okay, it's super accurate but not
there were other measures.
especially when you're doing things that are a bit more complicated text.
Yes, fast. Wakolot.
Accuracy is not the best.
You want to move thinking.
Guys, Jupiter is the birds. Wait, yo.
No, I'm saying even
It's not the same.
Oh, they were sending to
So you still
everyone.
can find the X.
yeah, there's one.
Magabaru said like a true school and this bus is not enough.
But that's the X to P.
That is expensive, eh?
But then it should still have that.
Imagine an bus not big enough. Where are you going to take the money?
It's not going to be
She said might not be enough.
There's the X one.
From parents. What if your parents are broke?
What are they saying? They're selling reminding people to apply for instance, but the money is not enough.
No. See when after this code, a bit like just there should be I think this line is missing.
Yeah, those are the things.
Also,
Like array parts.
This thing is big.
Visualizing. I always have a problem with seeing. You see, like I hate if statements and for loops in Python. Like in Python in general, I can't see them. You know, when it's just plus, it's almost like you put it in order. You do it here.
This guy.
I knew it.
It's the UG. Every single time you go.
Guys from UG. They're cool. guys from UG are cool. Let's ask this guy. What was the question?
what is this minus?
Accuracy the best metric.
Okay, guys, let's continue. I just needed to reply to this. Okay, so the
So, Korota 5,000. Yeah,
I don't know need to see your names.
guys, that's funny.
I want to see how much is it.
No, sorry.
This one, add this thing with this one. This is fine.
Okay, guys, then can we continue? She wanted to say something. So the question is that, is accuracy the best metric to measure or to evaluate our result? You're saying something or not? Awesome. That's quite very interesting. Very interesting answer. So she's saying, let's say, for example, you have an algorithm and you have a lot of money, which I don't have right now. And I want to give you guys all the loans. But somehow, there might be guys here who might not pay me here. All right. So I need to take that into consideration, put that as a metric. How many times can my model or my algorithm predict or candidates who are not going to pay me? Did I put that right? So is it better or I don't know, or worse? False positive. Okay. But okay, I see what you're saying. More like a confusion matrix stuff. Okay, that's the best answer. But we can have a better answer. Let's ask another person. Who wants to answer? Who wants to volunteer? Okay, let's continue then. Okay, so yeah, like she said, it depends on the problem. And in our case, specifically, we don't want to be in a position whereby, I was saying to this gentleman earlier, where you, now we'll see that later. Let's just pause for now. I'll just answer that question later. So, here we just predicted, we did not split, we did not do anything, right? But now we want to get a measure of how well are we doing, right? Using the same structure like everyone was doing, like Vaughn and Antonius and the rest. We just chose 3 because I like number 3. And I just kept on changing the numbers and it kept on giving me the highest accuracy. That's just, what number should I choose? 7. Let's see. Okay, something's crashing. I need to run this. What accuracy do you guys have there? 82. Right? On 3, when K is 3, what's accuracy do you guys have? 83. Oh, yeah. So now, accidentally, I just put 7. Yeah, my accuracy went up. Huh. Does anyone see something wrong here? Then the first question, what is the best value for K? That should be the question that we should be asking ourselves. Because if you guys were sitting in this group, this guy likes Cristiano Ronaldo, let's put number 7. Other person, me, I like Messi, let's put number 10. And now I was like, no, I like 42. And now everyone can just put a random number just to get the best accuracy. And if you have time enough, you can start at 3 and go to 4, go to 5, go to 6, go to 7, up until you get the best accuracy, right? Wait, hang on, that's an algorithm. Right, so I can write a for loop and feed in K several times and see which one gives me the best accuracy or the highest accuracy. And that's my best value for K. Right? So now we have some sense of justifying why we're choosing certain values. Right? So the K is it's a hyperparameter. We need to choose it, right? Like to so now here's something quite very interesting, and I need you to guys take note of this, and especially when it comes to accuracy. So if K is small, the model is complex and can lead to overfit. Right? So what is overfitting? Let's ask someone who hasn't said anything. Gentleman can answer us. How do you know when it overfits or not?
Bias is high and variance is low.
Yeah, you guys have nice stats. Bias is high, variance is low. How do you know? The question is, remember, you guys want to build models that's going to kill people, right? How do you know that your model is actually performing at its best, or is it overfitting, or is it underfitting? So we're going to answer some of those questions there. But another answer? Huh? Oh, yeah. Okay, he's going to answer us when accuracy is approaching 100%. What if my algorithm is actually 100%? Okay, my question is this. Let's say I've got a robot. This robot is carrying gold. Right. Nah, that's a bad example. Let's go to Uber. Let's say there's a self-driving car, right? Now, in this car, there's quite very expensive materials and stuff and things like that. So, performing at 82%, 84%, or 85%. So 15% of the time I'm going to crash. So I'm going to crash once, all the equipment is gone. Right? So my question is, what if really I need 99.9%? What if I really need that? How can you tell whether I'm overfitting or my model is performing very well? So we're going to answer that later as well. You wanted to say something?
Yeah, I wanted to say, you know, when it's not able to
that's a good answer, but how do I see it here? How do I see it in the notebook? That was my question. How do I see that? Nah, this thing is overfitting, right? So you need to be able to see that in your notebook, like, nah, this thing is actually overfitting. Want to say something? But that's a good answer, and also that's a good answer. The test size. This guy is something quite very interesting. What does this thing do? So he random state 1. I'm gonna explain what this thing does. So some of you can Google. Yeah, you wanted to see something. Why would you want to generate the same? But I can put 42 here. But what does it mean? I hear what you're saying, but what does it mean? Remember, guys, you need to understand, right now you need to dive deep into the data and see these numbers, they must be here. Remember, these things, when you look at this, you must actually see what is this 0.8 for me, right? So I can actually tell what it means, but you need to, yeah, that's quite a very good answer. So you're right, it generates the same the X training and the test set, right? Each time you run this algorithm. For example, if I change this, if I remove this, right? Watch. Now look, my accuracy went to 279. I'm not sure if you guys are seeing what I'm seeing here. There's something happening with this data that I can't grasp. Understand? And those are the smaller things that you need to find, right? Let's run it again. You see the accuracy is 79. Let's run it again. It's 84 again. What's happening there? Choose a random test. Yeah, that's a good example. But why would I want to have it whilst I'm building my model? Yeah, take from the same kind of pool. This gentleman gave me a good answer. So when you do this, don't forget to put your random states there. Went back to 74. Let's say hello to Gary.
Hello.
Okay, now, so remember we ask ourselves 2 questions. How do we know when it's overfitting and how do we know it's underfitting and stuff? We can run the algorithm that you just said, right? Move from 1, press 2, press 3, press 4, press 5, press 6, press 7, press 8, press 9, press 10, and write them down maybe in an Excel sheet. And once you're tired, after reaching k less than number of your values, and you can just go back and choose which one is that, which is a for loop, right? So for every value that is there, just change the value of k, increment the number of times, and fit, train, and push that into the array. That's it. So that's what this thing does, and just plot that array and see what it does, and you will see that actually you should have chosen 2, which has 0.86. Does anyone see why? 2 is there, and which was there. Now, I asked a question about overfitting and underfitting. Remember, when the value of k is small, it means what? Let's go back to our it was written somewhere here. Okay, in literature, right, it says if K is small, the model complex can lead to overfit. Guys, do you see what's happening here? Right? The best value for K is 2. So, and I have the highest accuracy there. Immediately, I know I'm overfitting. Right? I know I'm overfitting. How do I know that? If you read the literature, and if the value of K is too big, now, big in what sense? Remember how many values do we have? It's 310, right? So within that range, so your data set could be thousands and thousands, so you just need to get the idea. And we just chose the first 25. We could have made 50, up less than the number of points we have in the data set. So what we have learned so far, we've learned our supervised learning, we've done exploratory data analysis, we've learned K and N, just predicting without splitting the data, how to fit, and how to measure the accuracy, and how to choose the hyperparameter K. So is this helpful a bit? Just a bit, right? Now, one would agree with me that we need to find a way to find the most perfect value. Not perfect value for K, but a value that does not overfit or underfit. Just the correct value. It exists somewhere here, right? And we don't know that, so we need to justify it. So later I'll show you how to do a grid search. To search that. But before that, let's look at regression and check what we've learned so far. Remember when we started, we had this scatter matrix, and I said sometimes I would want to build a quick model, maybe might perform better than the k-means by just looking at lesser features, maybe 2 or 3 features. But in this case, I will have 2, because I can see some of them, they have a linear relationship, and some of them, they have some circular relationship, looking at the normal and the abnormal. So you will see that normal people, they are around there, and each algorithm behaves differently. So you have to build a model for each one of these cases if you want to use them separately, right? There's 2 features. So the most easiest one is for now, is linear, right? Let's go for linear. You can also do complex ones like circular stuff. Okay, so if you go back to the scatter matrix that I've shown you, I just chose these 2 because by just looking at them, it was just me just looking at the scatter matrix and assuming that there was a linear relationship, because you could see it was something like that. You could choose other ones that you see that they have a linear relationship and try compare with this one. Yeah, you can see it's something like this. So you can clearly see that there's a relationship between a pelvic incidence and a scalar, sacral slope. So if I wanted to build a simple model, instead of making it complex, I can come measure your sacral slope and your pelvic incidence, and I can have a level of confidence to say whether you normal or abnormal, right? Just using y equals to x plus b. And we need to learn that machine learning is not something more complex than this. This is machine learning A to B, ends there. It's just that when you use other algorithms, it gets more complex, right? But a machine learning algorithm is just y equals to x plus b. There's nothing else. It's just that you have some input and output. The only thing that gets different is that sometimes you cannot represent this equation to human being, do deep learning and other stuff, right? But essentially, it's just y equals to x plus b. So where a is a weight and x is some input. If I put a 2, maybe I get a 7. If I put a 3, I get a 20. And that's a general model, like he was saying there. It's a general model. It will never change. And people think machine learning is this model that changes. It's that model that generalizes the environment. And it's just y equals to x plus b. That's it. It's just that it has an answer for every input that we have. So in the linear regression, we use the R squared. And you can follow this. And you can see by me just looking at that, my R square score was 0.64. Based on the two inputs, the features that I chose. Meaning that, who can explain what does this mean? Anyone who's willing to explain what does R square score mean? Yes. Yes. Any other answer? Okay. So, like she said, shows that we have a linear relationship in how accurate it is or closer to 1. And the lesser it is to 1, we know that we don't have a linear relationship. So, from this, what can you take home? Is to say, this thing is gone. You can say, I can build a simple linear model and have a level of confidence to say whether normal or abnormal. And this is much more easier than what was built before, right? Now, this is what I was talking about, cross-validation. And now, we need to look into this. There was a guy who said that, I think it's that guy, he said, our accuracy depends on how I changed my test data, right? The test set, right? The test size, okay. Test data, so test size, cool. Test set, okay. Test size, okay. And it's in, okay, test set. And he's somehow right, because one group might say, no, why are you choosing 30%? Another group is like, why are you choosing 20? And now it becomes a challenge to say what test size is suitable for my data. Who knows what test size is suitable for which data? That's a question. So here, you're answering, sorry. So here, we want to say, if we were to split our data 5 times, and we get different accuracy, which accuracy are we going to use? Right? So the question is that if we were to split our data 5 times, right? So you agree we'll get different accuracies, right? Now, which accuracy are we going to use? Maybe we get 0.89, 0.9, 0.91, 0.92, and 0.93. Which accuracies are we going to use? And maybe we're like, let's split it for the 6th time. And we don't know what's going to happen. So k is the number of folds. When k increases, this is computational costly, so it will take some time to run. Here's something quite very interesting when we run the cross-validation for our linear model. Splitting it 5 times, we get different scores. Where our scores was the R squared. Right? So we first did it, and we got 0.3. And we did it again, we got 0.61. Or this is 0.64, I don't know what point was this. And we did it again, we got 0.5, and it was worse. Does somebody see any problem or some insight or why you would want to do this? So, for example, if you did not do hyperparameter tuning or cross validation, you could have easily chosen any value and got that R squared and tried to improve it, and it doesn't improve, and like, no, this data is not linear, and it doesn't improve, and like, no, we need more data, and it doesn't improve, or just improves a bit, and you might have found that maybe your test set, or you should have run your cross validation, or you could have done a better hyperparameter tuning, and voila, your R squared increases, right? And you can see that our average is at 0.4. So the question is this a best linear regressor or best linear algorithm to choose? A question, right? So remember we split it 5 times and we got this result. So we're averaging at 0.4. So, which is not quite good. Now, where is that lady? Oh, she's sleeping. She was speaking about cool stuff. False positive, right? Okay, these numbers might have changed. Actually, I know this can be boring. Now, who knows what a confusion matrix is? I know it's confusing. Confusion matrix. Remember, our goal is to find the best parameters for our algorithm, right? And we saw that using accuracy could not be the best. It's not. So that we got the highest accuracy, but our model was overfitting. Then we use cross-validation to be like, okay, cool. Which which using this our linear regression, getting the R score and splitting it 5 times, what scores did we get? And now we kind of like getting an insight of what's happening with our data here. But we need to find a way, how well is it classifying the false, she said false positives, right? And that's quite very important. Maybe you want to explain why maybe false, in this particular case, it's important. Anyone, why it might be very important to look at other things except accuracy, especially in this data set? Why would you want to do it? It's sensitive. Okay, so let me explain this a bit. So 0 being normal, 1 being abnormal, right? Maybe I could be making a mistake. Okay, it could be vice versa. 1 being normal, 0 being abnormal, but vice versa. So if you look at this diagonally, it shows the number of corrects that you've got in that particular category. So if the things that you said, the things or the patients that were classified as normal, whereas they were normal, they are 58. You're sure about these ones. And the patients that were abnormal, whereas they were truly abnormal, they're 21. Here's some interesting facts. So there's a problem. There's people that we say they're abnormal, and whereas they were abnormal, whereas they were normal. So I'm going to ask this question. Which case do you want to be? Do you want to say, is it better? Yeah, maybe I should ask this question. Is it better to say you are normal, right? Let's say you remember you went to, this is the algorithm that I deployed with data scientists, and the orthopedic surgeon used it, and you got an accuracy of 86. And I got there, get there, they take measurements, doctor presses predict. And now here's the question. Is it better to say, am I normal? Where else, like, in true form, I'm abnormal? Or the algorithm says I'm abnormal, or else I'm normal. So which case is better?
Depending on the case.
None. Okay, let's use an extreme case. So which case, let's say you're talking about cancer. I go to the doctor says, yo, person, you've got cancer. Or else I don't have it. Or I go to the doctor and I'm like, yo, person, you don't have cancer, dude. And I actually have cancer. Which one is worse? The first one.
The first one, yes. The first one is better.
The second one.
Why the second one?
You won't diagnose me.
Okay.
It's better to die.
It's better to die, not to darling.
Alright, let's discuss that. Let's take a 5 minutes break. We're about to finish. Let's discuss that.
What are we discussing?
Which case is better?
Better to prescribe medication to someone who's not
So we're having a bit of an argument with this,
yeah.
Listen to her.
Discuss with your
Phase
friends.
2 is okay. But it's better to die not knowing you have cancer.
Discuss.
You see the note that was cooked.
So what if they have like detected it earlier so that they can treat it? Remember, cancer can be but you're not. Oh. Oh, okay. But you're sick, yeah. That one is
Oh, but it's, I feel like it's
I'm not trying to justify that.
I don't want to be told I'm sick when I'm not sick.
Yeah, but at least it's not gonna happen.
But at least it's nice when you hear you were not sick. Yeah, at least you can imagine, I'm fine, I'm perfect. Sick, yeah. I think I've seen a study on a similar thing, but it was for alcohol. They made people drink malt beer, so it's not alcoholic, né? But they confused them that it's beer.
So it was placebo.
So people were like, yeah, it's like a placebo thing.
Yes, man. Please help me. Professional.
Hey, this guy.
Basically, accuracy is the best measure.
Hey,
Measure should
you're not doing it right.
Not necessarily, but
Disprove me. Come on, explain to me how am I wrong.
I can put.
We're having an argument. Yeah, please help us with something. Yeah?
I discuss with the class.
No, it's private.
ML. You know what I'm the link is on.
Okay, ask the
I'll
class.
tell you a story before you guys.
So how do you know automatically that your what's this false positive are low?
Because remember, what makes your model not 100% accurate? Because there's false positive. So that's why accuracy is not 100%. So that 40, let's say our model is 86% accurate, right? You see those false positives that you see there? That's the 14% inaccurate that it is. But then your accuracy will also consider the miss rate, does it?
The what?
Does, right? Like your miss rate, those that were not classified.
Let's Google these things.
He left. Did he leave? I think he's gonna make What the phone is it?
Yes, it does.
It does. It doesn't make sense to say. What if they did? Guys.
It considers everything.
That's what accuracy considers.
Yeah.
So which one is our best measure of, which matrix should we use to best measure our thing?
The thing is,
The other half
You must be accurate.
but then when we get there, the accuracy, we tend not to see
Who knows Alzo?
You're like, yeah, the accuracy is 7%.
And then you're happy.
And then you're happy like that. Oh, it's perfect.
Danzo. You know a guy called Danzo?
watch this other video.
It can't only depend on accuracy, really. Because what if accuracy is 76%? Then why have
But with
it is a good accuracy. Yeah, it is a good accuracy. Then what happens? Why is that then?
Or they just
they give you accuracy bar as it
No,
is.
that's why I must
Yeah,
know
but-
that there's something's not.
But then, me knowing how many false positives
so
are
it does
there,
this whenever-
when I know that my model is inaccurate, right? It's not 100% accurate. I know
Yeah, I think somehow it does
I don't
some
need to know
pausing
Because
things.
then now, what if my real life data now I'm using 18,000 records? I need to know that 15 of them are
So what are you
inaccurate.
saying? But are you saying that when you give someone are they really considering the true person?
It's fine. We'll just do the other.